Welcome to the lecture 19 of the course Modeling and T-CAD Simulation of Solar Photovoltaic Cell. In this lecture, we will discuss different losses in solar cell. In the last class, we have discussed origin of series and shunt resistances and effect of these resistances on the IV characteristics and hence on the performance metrics such as open circuit voltage, short circuit current, power conversion efficiency, etc. Also, we discussed and we have drawn the equivalent circuit of solar photovoltaic cell without considering these series and shunt resistances and including these resistances. In this lecture, we will describe several losses in solar cell. They are mainly categorized in two categories, that is optical loss and electrical loss. In optical loss, we will mainly focus front and back surface reflection, and electrical loss, it consists of Shockley-Red Hall or in short SRH and Auger recombination. Carrier recombination in a semiconductor are different types, but we will mainly focus here Shockley-Red Hall recombination and Auger recombination because these are dominating in context of solar photovoltaic cell. Optical loss. You know, when light faces an interface, that is the interface between two media of different refractive index, it gets reflected. Some portion of light is getting reflected back to the first media when it is traversing from first media to second media. The same thing happen here because solar cell is basically made of semiconductor material. When solar radiation incident on this device, light faces interface between air and semiconductor, and air refractive index is 1 and refractive index of semiconductor material is more than 1, say 3, 4, etc. So in the interface between air and semiconductor front surface or solar cell front surface, there will be a reflection, and the portion of reflected light back to the air will not be used for absorption purpose in a solar cell. Suppose this is a solar cell structure. Suppose we have solar cell front surface like this. So the incident light H nu, if the front surface reflectivity is R, so some portion will be reflected back and the entering part will be 1 minus R into the intensity of the light. For silicon semiconductor based devices, the refractive index of silicon is 3.5 and air, you know, this 1. So due to this mismatch between refractive index, there will be reflection from the front surface. At a normal incidence, the reflectance R from the front surface, it is denoted as NAR minus NS by NAR plus NS whole square, where NS is the refractive index of semiconductor material. If we calculate this value for air, that is 1 and semiconductor 3.5, it will be coming the value of reflectance. Let us draw here the picture. This is the PN junction solar cell. Incident light this portion is entering and R is the reflected back. So 1 minus R is incident into the device. So carrier generation process we have discussed so far few class before, that Gx, what is the rate of generation per volume per second, that should be multiplied by a factor 1 minus R of the intensity. So the generation rate can be expressed including the front surface reflection 1 minus R into alpha into Ix, and Ix is nothing but I0 e to the power minus alpha x. I0 is the intensity of light at the incident point, and this generation rate is at any point x. Also the intensity can be replaced by incident power, optical power P incident divided by area into h nu, if h nu is the energy of a single photon, A is the area where it is illuminated. So this is the final expression for generation rate at a position x, including the front surface reflectivity. So from the expression it is clear, due to presence of this R, front surface reflection, generation rate will be reduced. So this loss is called front surface reflection loss. And the formula, if you know, if P incident is given in watt, then h nu, if it is given in electron volt, you have to multiply h nu value with the electronic charge 1.6 into 10 to the power minus 19, and then this term, total term, gives you number of electron hole pairs generated per volume, that is per meter cube per second. And if you calculate this for 3.5 ns value, almost reflectance will come 31%. If you calculate this value, considering the refractive index of semiconductor Ns is equal to 3.5, so it will be, reflectance will be coming as 1 minus 3.5 by 1 plus 3.5 square minus 2.5 by 4.5 square, and in percentage you have to multiply with 100 with the fraction. So this much reflectance, the order of 31% will be coming. Now let us come to the point of electrical loss. Now let us come to the discussion. Now let us discuss the electrical loss. Basically, electrical loss is contributed by carrier recombination. So out of the photogenerated carriers, all cannot be separated out at two end points. There are some recombinations. Due to this recombination, carrier loss will be there. And there are 4 types of recombination is observed in a semiconductor material. First of all, this is direct band-to-band recombination. Second is indirect recombination through trap states. Third is Auger recombination. And fourth is surface recombination. We will discuss one by one. So direct band-to-band recombination, this occurred mostly in the direct band gap semiconductor. And this generally gives you the radiation, that is, this recombination is radiative recombination. And band to band means the conduction band to valence band. Suppose you have a conduction band minima and valence band maxima, and if it is a direct band gap semiconductor, in EK diagram also you can see the position of the minima in the conduction band, and in case of valence band they lie in the same K value. So this band to band recombination gives you radiation. This band to band recombination is not very important for solar cell, because in case of solar cell we use indirect band gap semiconductor, say silicon, widely. If we use also direct band gap semiconductor, then also this will not considered as a part of loss. And if we formulate these things, the recombination rate, that is a rate of change of carrier or electrons, say in n-type semiconductor, dn dt, that can be written as alpha r ni square. Why? Because generation rate in a semiconductor is alpha r into ni square, and recombination rate, which depends on the presence of carriers, holes and electrons, that is n and p after generation, into alpha r. This alpha r is the recombination coefficient. Its unit is centimeter cube per second. Here you should remember Pt, there is a at any point time, at any time t, say Pt will be P0 plus delta Pt, and Nt also will be N0 plus delta Nt. N0 is the equilibrium value, P0 also equilibrium value, and after generation due to optical incidence, delta P amount of excess holes are generated, delta N amount of excess electrons are generated, and they are equal because electron hole pairs are generated in the form of pairs. Now, if you put these values in the equation, P0 plus delta P and N0 plus delta N, you are getting this alpha R N0 plus delta P, P0 plus delta P, and after multiplication and algebraic simplification and using these relationship delta N is equal to delta T, you can get the final expression. Also you have to assume the low level injection, that is excess carrier, excess minority carrier much greater than the majority carrier, delta N much less than P0, and also in a p-type semiconductor N0 is much less than P0. Here this assumption, low level injection assumption, is written for a p-type semiconductor. So excess delta N will be less compared to the majority carrier concentration. Also the equilibrium minority carrier concentration, that is electron, is much less than hole concentration. If you apply these two assumptions, and also if you expand by putting the value of N and P by N0 plus delta N and P0 plus delta P, and if you multiply this term, you can get this expression. Nt, actually ddt of Nt, N0 plus delta Nt, N0, ddt of N0 is constant, so ddt of delta Nt will remain, that is here. And in the right hand side, one term will be appearing alpha r into n0 into p0, and you know alpha r n0 p0 that is equal to alpha r ni square, because n0 p0 product is nothing but ni square. So using this, the ni square term related these two will be cancelled out, and after assuming these, after putting these assumption, you are reaching the expression this one. And if you solve this equation, differential equation, its solution gives you the delta n with time will be some capital delta n dc value e to the power t by tau n. It is minus actually. That means after generation it gradually decreases with time. So delta n e to the power minus t by tau n. Tau n is nothing but carrier lifetime. Which carrier lifetime? This is electron lifetime, that is minority carrier lifetime, which is defined as alpha r p0 inverse or 1 by alpha r p0 in this expression. So this electron recombination lifetime in a p-type semiconductor, or simply it is called electron lifetime. Similarly, this type of calculation you can do for a n-type semiconductor for minority hole. In that case, whole lifetime will be obtained as alpha r n0 inverse. In case of these assumptions are not valid, that means n0 much less than p0. That is, if you consider the semiconductor is not sufficiently extrinsic, in that case lifetime expression will contain both the term n0 and p0. This is the general expression, that will be 1 by alpha r n0 plus p0 in that case, which is approximated to here in case of highly p-doped semiconductor, because here p0 is much greater than n0. But you cannot assume this if it is not sufficiently extrinsic. That means if the semiconductor is not heavily doped, these assumptions cannot be taken. In that case, you can use the formula for lifetime will be like this. Now let us come to the discussion of indirect recombination through trap states. In case of indirect band gap semiconductor, this recombination takes place mainly, say for silicon. In this case, recombination of carrier cannot take place without the help of a defect states or a trap states, which is nothing but energy level or allowed energy level in the forbidden gap of the semiconductor. Probability of direct band-to-band recombination is very low in case of indirect band gap semiconductor. Why? In case of indirect band gap semiconductor, there is a mismatch between conduction band minima and valence band maxima, mismatch in terms of k. So valence band maxima may lie at k is equal to 0, but conduction band minima does not lie at k is equal to 0, at a different k. So for direct band-to-band recombination, conservation of energy as well as conservation of momentum are required, which is less likely. That's why we consider no direct band-to-band recombination takes place in case of indirect bandgap semiconductor. How recombination takes place in case of indirect bandgap semiconductor? Recombination occurs through the presence of an energy level within the bandgap, and that is called defect state. These defect state may be present due to impurities, due to crystal defects, particularly at the surface. There are incomplete bonds for any semiconductor material. So if you observe the band structure, band diagram for a surface region, there are some energy levels allowed in the energy gap, band gap. Also there may be other impurities or any defects in a crystal. Instead of a regular array, so some atoms are missing or some different types of atoms are putting there. Even an impurity which is doped for making the N-type or P-type semiconductor, that is also an impurity. So due to these reasons, there may be some defect states or trap states in the energy gap in an indirect bandgap semiconductor. And carrier recombination takes place through these defect states. That's why it is called trap assisted or defect state assisted recombination. Now the defect states or trap states, they may lie at the middle of the band gap or they may lie in the gap but closer to the conduction band minima or closer to the valence band minima. So based on their position, the defect states are categorized into two categories: shallow defect states and deep defect states. Suppose this is conduction band minima and this is valence band maxima. This is the position of intrinsic Fermi level EI. Defect states may lie here. Some defect states may lie here. These are the allowed energy states due to impurities. But defect states may be here also. The defect states which are very close to the valence band or conduction band, they are called shallow defects. So these two are shallow defects. But this defect state is called deep defect states. Generally, 3 kT value is taken as a boundary for deep defect states and shallow defect states. That means if the defect states lie within EC minus 3 kT to EV plus 3 kT in this range, then it is called deep defect states. and carrier in the conduction band may trap or may recombine through the trap if there are some deep defect states. Generally, the shallow defect states are called trap states, but not recombination center, because mostly in case of recombination, deep defect states are required. Although there are some other factors which determine whether carrier will recombine through deep defect states or shallow defect states, but mainly it is seen that electron hole recombination takes place through deep defect states, not through shallow defect states. And the trap assisted defect was first described by three scientists, Shockley, Reid and Hall, and thus as per their name it is called Shockley-Reid-Hall recombination model or Shockley-Reid-Hall recombination, in short SRH recombination. The very famous recombination is called SRH recombination. Now, how this SRH recombination takes place? What is the process of recombination? There are four processes are involved in this recombination. One is called electron capture, hole capture, electron release, hole release. Let us draw these three processes in a figure. Suppose this is a defect states. Electron in the conduction band may be captured by this trap state or defect state. This is called electron capture. Also, when electron moves back from a trap state to the conduction band, it is called electron release. Then hole capture. Hole capture means holes from valence band moves to the trap state. Hole movement means in opposite direction there is a movement of electron. This is called hole capture. Hole release means hole should release from trap state to valence band. So hole should go back from trap state to the valence band. Hole is going back from trap to valence band. That means electron is moving from valence band to trap state. Same thing. Hole release. These four processes are involved in recombination. Now, suppose one electron is captured by the trap state, that is, electron moves from conduction band to trap state. After this electron capture, if there is a hole capture process, So holes are also moving from valence band to trap state. Then this electron and this hole will recombine here. That means recombination from conduction band to valence band takes place by two processes: electron capture followed by hole capture. But if the electron after capturing they release and emitted back to the conduction band, this will not be further recombined. So there is a continuous process of capturing, releasing are taking place. So on average, some of the captured electrons may be recombined with the holes, some may be released back to the conduction band. So for a recombination, electron capture followed by hole capture is required. Suppose Nt per centimeter cube is the density of defect states. Instead of single states, if we consider there are several such defect states. So what is the density of states? I also defined that density of states means number of such states per volume per energy interval. So Nt suppose the defect states at a location, say Et. So this position, suppose Et, I mentioned the position Et. There is a trap state energy. And this is near the mid gap. If this trap state is near the mid gap, then probability of this electron capture and hole capture is the maximum. Otherwise, what would happen if there would be a very shallow defect state? After capturing electron from valence conduction band to the trap state, it may release back to the original position. So they may not be taking place in the recombination process further. That's why it is assumed that the defect states which is at the deep are responsible for recombination of carrier from conduction band to valence band, transition through defect states. Now what is the rate of electron capture? If Nt and Et, Nt is the density of states and Et is the position, rate of these capture, electron capture, is proportional to two things. One is carrier density or electron density at conduction band, and also the fact that the trap state should be empty. So conduction band should be filled, trap state should be empty. This is the condition for electron capture. So electron capture rate can be written as Vt n sigma n. I am coming to that. Initially, actually, this is n. N is nothing but carrier electron concentration in the conduction band, and 1 minus FET. What is this 1 minus FET? 1 minus FET is the occupation probability at ET level. So 1 minus FET is giving you the probability that trap state is not occupied. So product of n and 1 minus FET, this REC is proportional to this product. But there will be a constant, and that constant term is nothing but sigma n Vtn into Nt, where sigma n is known as the electron capture cross section for this trap state. Electron capture cross section means an area around the electron, so that if holes come into that region, they will be recombined. They will be affected by this electron. So this is called capture cross section. And Vtn is the thermal velocity, Nt is the state density, defect state density. If you take the multiplication of sigma n, Vtn and Nt, you see this is area. This is also centimeter per second or meter per second. So area into this centimeter per second, this is a volume per second, and this is per volume, Nt per volume. So per volume, this is a cancel out. Ultimately, this is a per second. So electron capture rate can be written as in this way. Here the thermal velocity Vtn that can be obtained from this relationship, that is 3 kT by effective mass of electron. For whole it will be mh star, root over of that. So this is basically the thermal velocity, that is a temperature dependent parameter. How electron moves with the due to the thermal energy. Anyway, now electron release probability or rate. How electron release? Electron release, if you see in last this electron release, that from trap state to conduction band. For this happening, trap state should be filled and conduction band should be empty. If such situation occurs, some states are vacant in the conduction band and this state is occupied, then the electron release may occur. So rate of this electron release can be written as some constant into f of Et Net. F of Et means is probability that Et is occupied, and Nt is multiplied. If Et into Nt, this gives you the total carriers at the trap states. En is the proportionality constant. So probability is proportional to the number of field defect centers and number of empty states. Thus RER proportional to FET NT, and proportionality constant is removed by a multiplying a factor, that is En. En is constant. Similarly, hole capture. Again, hole capture means actually the transition of electron from defect state to valence band. So hole capture can be written as sigma p VTP into NT into P F of ET. Here for hole capture, that is for transition of electron from defect center to valence band, defect state should be occupied and there must be one empty state in the valence band. So F of Et is here, not 1 minus FET like electron, and NT. Hole release, similar to the electron release, hole release can be written some constant into 1 minus FET NT. Here 1 minus FET, why 1 minus FET? Because hole release, for hole release, defect center must be empty. Hole release means transition of electron from valence band to defect center. Hole release means hole is releasing from trap state to conduction valence band. That means electron is moving from valence band to trap state. Yes, it is written. And from valence band to trap state, so trap state must be empty. So trap state empty means 1 minus F of Et into NT is the occupation probability. So this is proportional to RHR is equal to EP into this. At equilibrium, the electron capture and electron release, they must be equal. Otherwise, there would be accumulation of electrons either in trap state, or there would be a decay of electrons in the trap states. But this is not the allowed thing, and this not happen. That's why capture and release, their rate must be equal. Similarly, hole capture and hole release rate must be equal. If you put this value equal from the expression, you can reach this expression. Now F0, FET and this value we can solve, or we can write the simplified expression by considering that FET say F0 ET, say equilibrium condition. Equilibrium is denoted by suffix 0, that's why. So FET is replaced by F0 ET. Then by equating REC and RER, you can get this expression. In this expression, we now have to put that value of F0 ET from the Fermi-Dirac distribution. This will be 1 by 1 plus exponential ET minus EF by KT. If you take inverse, so 1 by F0 ET, that will be 1 plus exponential minus this. And if you take the only first term in after expansion, and if you neglect the higher order terms, it will be coming 1 minus exponential this rest term you are neglecting. So this is actually equal to sign, not approximation equal. This is equal to sign. This is almost equal to. And if you put this value again in this equating expression, this expression, you can get N0, that is equilibrium concentration of electron in the conduction band. So will be NCFC, NC exponential minus EC minus F by KT by taking the Boltzmann approximation. NC is the effective density of states. Using this N0 and this 1 by F0 ET expression, in the original expression, you can reach En, the constant term, can be obtained this way. The NC exponential ET minus EC by KT, this can be approximated as N1 for simplicity. So this will become sigma n Vtn. Similarly, considering the whole capture and whole release rate are equal, you can finally reach to the expression. You can try to solve this. All the steps are given and you can check. So EP will be coming this value. So these two final expression for coefficient constants, proportionality constants are obtained, and therefore the net rate of electron capture minus electron release. This is the net rate of electron capture in the trap state. That will be from the previous expressions, can be obtained in this way. Similarly, net rate of whole capture, that will be RH is equal to RHC minus RHR, whole capture minus whole release. This will be also this. So 46 and 47, these two equations giving you the net rate of electron capture in the trap state and rate of whole capture in the trap state. So what is the recombination rate? How can we calculate recombination rate? For recombination, we need whole electron capture followed by whole capture. This is the process. So at steady state, these two rates must be equal because electron and hole recombine in pairs. And therefore, if this would not be equal, this RH and RE, then there would be accumulation of electrons in the trap states or depletion of electrons in the trap center or defect center. That is not possible. That's why they are equal at the steady state. And the recombination rate can be written as R, either RE or RH. Both are equal. So RE followed by RH is required for recombination. So only one process is not possible for recombination. Net electron capture followed by net hole capture is the recombination process. So any of these rate, as they are equal, any of these rate will give you the recombination rate. RE and RH, these value from equation 46 and 47, if you equate them, you can obtain F of ET, that is occupation probability at trap state, will be this. And so R will be calculated by using this FET in any of the expression. Either you can use the RE expression or RH expression. RE expression is this and RH expression is equation 47. In any of these equation, if you put the value of FET, you can get the recombination rate. That will be simplified in this way. Pn minus Ni square divided by some factor n plus n1 plus some factor p plus p1. This is equation number 48, which is important, and this is the famous equation for Shockley-Redhall recombination rate. So this is the recombination rate. Here, these two terms are very important. What they indicate actually? If we define the whole lifetime tau p and electron lifetime tau n respectively in this way, say tau p is equal to sigma p VTP NT inverse. Why? Cross section of sigma p is the cross section whole capture cross section, thermal velocity, whole capture cross section into thermal velocity gives you the volume per second, and NT is the per volume, number per volume. So volume cancel out, this is a per second. So per second means second, if you take again inverse, it gives you the second. So this basically gives you the significance of carrier lifetime of hole. Similarly, tau n will be this. Capture cross section, I again repeating, capture cross section is an area around the carrier within which its opposite carriers come, they recombine. This is the physical significance. If you multiply with this thermal velocity, because electrons are always in movement, so that gives you this volume per second, some volume per second, that will be with the, if carriers, opposite carriers comes within that volume, they will be recombined. So if you multiply with this NT, there is a number trap states per volume. So obviously that gives you the time, average time, that indicates the carrier lifetime. If you put back this value, 1 by this is tau p. So finally expression will be tau p into n plus n1 plus tau n into p plus p1. And in numerator, this Pn minus Ni square, there is a excess minority carrier. Pn will be, P is nothing but P0 plus delta N, delta P, sorry. And N will be N0 plus delta N. If you put these values and if you take the product, some P0, N0 term will be coming. P0, N0 will be nothing but Ni square. That will be cancelled out with this Ni square term. Other term, say delta P delta N product, that will be very less, you can neglect. So you can reach a simplified expression further. Ultimately, by putting expression of tau p and tau n, recombination rate in a indirect semiconductor following the SRH is given by this equation. This is equation number 50. Now the Auger recombination, which is another, the third kind of recombination in a semiconductor material. Auger recombination is mainly possible for highly doped semiconductor. Here, highly doped semiconductor for direct band gap, it mainly occurs. This is a 3-carrier process. 3-carrier process means if a electron recombines with hole, there is a release of energy, and that released energy may be absorbed by the third electron to transit to a higher states. So this is the process here is shown. Suppose this is the before recombination. There are 2 electrons. So first these electron recombine with these holes. If it recombines with these holes, the released energy will be absorbed by this electron, and it will moving from a minima to the higher band. And as the energy released is in the form of Eg, this energy of this new electron, that's called high energy electron, will be Eg more than its minimum energy, minimum conduction band energy. So this is called 3-carrier process. So recombination and release energy is going to the third electron, and sometimes it is called EEH process in case of N-type semiconductor. Say for P-type semiconductor, in a heavily doped P-type semiconductor, so a hole is majority carrier. So electron hole recombination power or energy that may be absorbed by a hole to go to the higher energy state, and in valence band higher energy state means is lower. So this is the Eg value. So this Eg. This is called HH process, HHE process. This process is another process of recombination which is observed in a highly doped direct band gap semiconductor. And the recombination rate in this case can be expressed as some constant Cn into n Pn minus Ni square in a n-type material. In n-type material, majority is electron. Pn minus ni square is giving you the excess carrier generated, and it is multiplied with the n, because the rate proportional to the n as well as rate proportional to the extra carrier generated. So they are proportional in product form, and proportionality constant is Cn. So R will be this Cn for n-type material. Similarly, for p-type material, that will be reverse, Cp Pn minus ni square. Anyway, but you remember P and N again, P is P0 plus delta P, N is equal to N0 plus delta N, and also it is sufficiently extrinsic if you consider for n-type semiconductor. So minority carrier concentration is much less than majority carrier concentration, and in low level injection, if you consider the delta N and delta P both are equal, as well as the excess carrier delta P, which is much less than the majority carrier, then putting this value you can reach R almost equal to Cn N0 square delta N. Be careful, delta N, N0 square delta N. And minority whole lifetime associated with this process, because this is the rate. So whole lifetime, whole is recombined due to these extra electrons. So tau p will be delta p by R, and delta p by R is nothing but 1 by Cn, this R 1 by Cn N0 square delta N, and delta P are equal, so they cancel out, because tau P is depending on delta P by R, excess whole carrier concentration by rate. Rate is nothing but this, and putting as the delta N and delta P are equal, they are cancel out, 1 by Cn Nd square. Nd is nothing but the donor concentration. If we consider 100% ionization, so N0 can be written as Nd. That's why N0 is replaced by Nd. So this is the expression for minority whole lifetime in a n-doped semiconductor through Auger recombination. And in SRH recombination, we have seen different value of tau p, but for Auger recombination, tau p is different. Similarly, for tau n, there is a minority electron lifetime in a highly doped p-type semiconductor will be delta n by R, and it will be 1 by Cp Na square, where Na is the acceptor concentration. Now the last term is surface recombination. I told you the surface of any semiconductor behaves differently from the atoms in a well middle, because atoms in the surface has a different characteristics due to incomplete bond and other things. And this is the origin of defect states at the surface. Due to presence of these defect states, again some defect states are in the mid gap of the band gap, that will be responsible for recombination, and which that recombination is called surface recombination, as it is occurring at the surface. And for a holes in a n-type semiconductor, the surface recombination is determined by a flux of carriers flowing towards the surface. Flux of carriers flowing towards the surface. And in case of n-type semiconductor, that's why dp, there is diffusion coefficient, del p and del x at x is equal to 0, where x is equal to 0 indicates the surface. Pn means hole at n-type. That means del p and del x, x is equal to 0, which is nothing but Sp, there is a constant, into Pn at x is equal to 0 minus Pn0. Pn0 is the equilibrium value, and Pn value after generation, but at position x is equal to 0. This difference is proportional to this difference. So this will be Sp into this, and x 0 indicates the surface. Now Sp, the surface recombination velocity, is sigma p Vtp Nst, just like earlier, but here only difference is Nst is the surface density of defect states. That means number of defect states per area, not per volume like Nt. That's why Nst is mentioned here. And if you put is a cross section is square, centimeter square, this is centimeter per second, nst is per centimeter square, so 1 centimeter square cancel out. So dimension of vtp is the dimension of sp. So vtp is thermal velocity, that is a centimeter per second or meter per second. That's why the surface recombination rate sp is sometimes called surface recombination velocity also, but it has no relation with the actual velocity. Be careful, because the dimension is velocity of dimension of velocity, that's why it is called surface recombination velocity. Carrier gets captured at the surface state, which is lies within the volume sigma p tau p. There is a indication of sigma p into v tau p around the carrier. Similarly, for electron in p-type semiconductor, that is opposite dn del np del x is equal to 0. This will be Sn into np x is equal to 0, position minus np 0. Sn is surface recombination velocity for electron in a p-type semiconductor. So in this lecture, we have discussed optical loss mainly due to reflection from the front surface of a solar cell, and also some carrier recombination losses which are dominating in case of solar cell. The recombinations SRH and Auger recombination, these are two dominating processes. Other recombination, surface recombination is also important in context of solar cell, but band to band recombination is not so significant in case of solar cell. Surface recombination rate is sometimes called surface recombination velocity due to its matching with the dimension of velocity, but it has no relationship with the velocity. These are the references. Thank you.